Hi, welcome back to the lecture series on GPU architectures and programming. So, I believe in the last lecture we have been discussing in detail about a simple OpenCL host program, which is gradually looking into the architecture and discovering the different devices. And let us try and figure out now how after discovering the devices things are going to work. So, the way we will be interspersing the presentation is that before going into any segment of the code, we will be again kind of doing a small recap of the concepts we have discussed earlier, but we will do it in a more formal way, like we will enlist the properties of those concepts and why they are useful, and then we will be showing the corresponding program segments. That is how we will structure it. So, if you recall from our last lecture, here what we did was we have discovered the different devices. We are storing the GPU type devices in the for each platform. In the first part of the array we are storing the GPU type devices IDs, and then the second part of the array we have the CPU type device IDs. So, for platform 0, the first device, like in all devices, as you can see, all devices 0 0 0, in this the first device that you have is going to be a GPU device, right. So, let us say we get that device ID here in a device ID data type of type in a device ID variable of type CL device ID, right. Now, let us see how this can be used to do some real work. So, if you remember from our earlier lecture, so we discussed setting up a context, right, and then building up a context using devices that you slowly keep on discovering in the system and all that. So, now we are going to really do that using OpenCL code. So, what is really important is to remember a context is created and manipulated by the host using functions from OpenCL API, right. So, it is basically the OpenCL host program which is defining the context using the platforms and devices, and then inside the context the host program will perform interactions with the device. Inside the context the memory objects are also managed because you can manage, you can share data among memory objects sitting inside one context, right, because that is like an abstraction. So, for all the available devices inside the same context, the management of memory objects would be happening inside that context itself. It also keeps track of the programs and kernels that are created for each device, right. So, whatever devices you have created for which, what are the programs and kernels that are there, they are all managed by that context, right. Now, typically the rule is that you should limit a kernel to a given platform, because then you can fully utilize the system comprising resources from a mixture of vendors, because each vendor will provide you an ICD or the installable client driver, the OpenCL implementation of that vendor. So, that is a lower level library which will be running and managing the OpenCL code in that vendor's platform. So, if you need to limit the context specific to vendor specific platforms, right, and inside the context you can have multiple devices working together, which are also part of that vendor distribution. Now, if you remember earlier we discussed the idea of command queues, like why really we require a queue here, right, so that you can give an ordering of the commands and all that. So, that is also from a program's point of view, that is also a specific kind of data structure that would be you need to define for coordinating the execution of the kernels. Now, inside the command queue you can actually specify what are the queuing actions to be taken, which are the commands to be executed in which order and all that. Now, before OpenCL 2.0, commands could be enqueued only from the host. That means only the host can specify which kind of read, write or kernel execution operation is to be done. But from the OpenCL 2.0 specification, both host side and device side command queues, these concepts have come up, like a code that is executing in a device, like a device code would mean a kernel that is executing in an OpenCL device. From that itself I can create child kernels which can be enqueued directly from and directly, right? So we'll like to summarize like the device side command queue. You can have a host side command queue, you can also have a device side command queue, and this allows that you can spawn a child kernel from a kernel which is already executing on a device, and from this and you can allow the child kernel to be enqueued directly from the currently executing kernel, right? So this is essentially known as device side enqueuing. Maybe we will touch upon it later on. Right now let's go stick to the simple basics here. So in order to create any of these command queues, either a host side command queue or a device command queue on some specific device, there is a specific API that is used called CL create command queue with properties, right? So first of all, let's understand you need to operate in a part. You can have command queues defined at many levels. You can have command queues in a part device manner, right? You can have multiple command queues giving commands to a device, right? So in what are the possibilities? We'll see all those. Now you can also set the property parameter of the command queue in the CL create command queue command, like what kind of executions will be supported and all that. So this is just like a basic introduction to this structure called command queues. Now what are the properties that are supported? For example, you can have a property enable which is CL queue out of order execution mode enable. If you are setting this to be true, that determines that the commands in the command queue can execute out of order, right? I mean, sorry, it will be executing out of order. Also, you may be interested in doing some runtime profiling, like what amount of time exactly is taken by some read, write, or execute kind of operation on the device. So you can enable the profiling by using this flag CL queue profiling enable. To indicate that some command queue is a device specific queue, you can have this flag enabled. So only in such device queues, this is something important. We'll see later that only out of order queues are possible in devices. Now this other property CL queue on device default, which indicates that this is the default device queue and to be used with CL queue on device. Again, we will see such examples. Now there can be only one default device queue per context. So inside a context for a device, you can have one default device queue, right? So these are all again things specific to device queues. Like in a device, you can have a queue which is out of order enabled. For a device, you can have only one default queue like that, right? Now if it's not specified, an in order host command queue is created for the specific device, right? Nothing else is specified. You have created a command queue for a specific device. That's a host side command queue which is going to execute commands in the execution in the order in which they have been queued, not in an out of order way, right? So that's the default, that if you don't specify something else for a specific device, you have a host side in order command queue. So first of all, we will just see such simple examples. So you create a context and command queue. How does that work? So ideally for each platform which comes from different vendors, there will be one context and each device will have one command queue, right? For each platform, this is important, from different vendors. From each platform you have one context and each device will have one command queue, right? So using that command queue, we are going to give commands, read, write, execute kind of commands to the device. Single device can have one or multiple command queues. Now that's also important, right? You can have multiple command queues for the same device, but what's not possible is a command queue can be associated with only one device. I cannot have a command queue which is churning out commands to execute in multiple devices. We'll discuss this thing later, right? So for this example, we have created only one context. We'll create one context and we'll create one command queue for the single GPU device which we chose right here, this one, right? So here, as you can see, for the 0th platform, we have chosen the first GPU device, and for that GPU device, we will be doing all these definitions of context, queues, and all that, so that I can create a context, pack the GPU device inside the context, create a queue which will be enqueuing commands targeting that device and all that, right. So, one thing one must appreciate while we go through these concepts is how generic this system is. I will just repeat that you should not get overwhelmed with such lot of definitions. Let us understand that this has been kept like this, so to make it generic. It can execute so many different kinds of devices coming, I mean, if you have multiple devices arranged together, you can, so this gives you a way to organize their architecture, schedule programs on them, and create dependencies and all that. Now, of course, the other important point would be, while this code looks so difficult, most of these are kind of very, I mean, going to be repetitive in the context of program execution. So, those can just be copied if you have one implementation available with you. So, the first thing that would come is how to create a context, right. We have been talking about context. So, this is the call for that. CL create context is going to return you a OpenCL context, right, and it can go through several parameters which are specified here. Now, initially when you are just creating the context, we are just we will just discuss that we just specify what are the devices to be attached with this. In this case, we are just giving one device, right. So, we just have a single pointer to that device's ID. If I have a collection of devices, this would essentially be an array of pointers for that, right. So, I have just created a context with one GPU device. In general, as I am repeating, I can create a context with multiple devices, multiple CPUs and GPUs kinds of devices and all that, by creating a device ID array and passing it right here, right. The next thing that comes is I have to create the command queue, right. So, this would be the command for that, CL create command queue with properties, right. So, you are creating a command queue for this context which has been provided, right. And since we have discussed, so that inside a context I can have multiple devices. For each device I need to have at least one command queue which will issue commands for the device, right. So, we will create now that command queue for the context and also for some specific device in the context. I am trying to impress upon why we should also have the device ID here, because although here I am creating a context with a single device, I could have created a context in general with multiple devices. So, then when I am creating command queues, I need to specify for which context, which device I am creating the queue, right. So, the next thing would be a program object. So, an OpenCL program consists of a set of kernels that are identified as functions declared with the kernel qualifier in the program source, right. So, you will write the OpenCL kernel with this qualifier kernel before the declaration, as you can see in our OpenCL vcat kernels example. Now, the program executable can be generated online or offline by the OpenCL compiler for appropriate target device. As you can see, one option is, like I said earlier, the kernel can be specified inside in a way that finally the host program would view the kernel as a character, as string, right. Now, so it will look at it like that, and it will compile it and then create the program object and then create commands around it. Now, this idea of creating the program object, we are saying that it can be generated either online or offline by the OpenCL compiler for a suitable device. In this case, we will just show us vanilla host code, where the kernel would be the code from the kernel source code. Creation of the program executable will be done online during the execution of the host program. So, what essentially is there in that program object? So, it is just like an encapsulation of the following information, like it would necessarily need a context, that the program object is associated with this context. That means it can access the data buffers and devices, on that context, right. It can be enqueued in the command queues which are on that context, like that, right. It will also have a binary or to execute, right. And the program object also have the successfully built program executable, or a library or a compiled library, right. And it contains the list of devices on which, as I am saying, that can execute. What are the build options for the program object? Right now we are not discussing that too far, you can look at it later on. and what are the number of kernel objects that are attached. So you can have multiple such kernel objects for the program object. Now, for creating such a program object for a specific context, there are some functions which need to be supported by the OpenCL API, and they are essentially this CL create program with source. The function of this would be that it loads the source code into that object. You have defined that object and you are loading the source code there. CL create program with IL, right? So load the code in an intermediate language into that object. Again, we are not going into the details of this right now. The next thing is CL create program with binary. You load the binary bits into the object. So essentially it depends on in what form the program is available to you. Is it available as a source, like as I said, a character array string, we will see some examples, or is it available in the form of an intermediately compiled language, like from the source you have made some compilation to an IR kind of representation, and from that you want to create the program for the program we want to create the program object, or even the binary is available and you want to just create then from CL program binary. So as I said, this idea of OpenCL online or offline execution would mean that you may perform runtime compilation, you may perform runtime intermediate code generation, or you may have the binary available. For all those three possible options, your host program will actually use one of these options to compile the program, to actually create the program object using the format in which the program is available, whether from source, from intermediate level code, or from the binary, right, for creating the program object. And then you have CL create program with built-in kernels. So this loads the information related to built-in kernels. You may have kernels which are already built in to load information about them, because those are already available to them. So the program object then doesn't need to create those kernel objects, but obtain the information about them. Now there are some other OpenCL APIs which are related to program objects, right? For example, you have CL build program. So what does it do? It essentially compiles and links a program executable for all devices or a specific device in the OpenCL context associated with the program, right? And then you have CL compile program, which is compiling the source, link program. So essentially, as you can see, you can build, it's a overall process, or you can program, compile, and then you can link a set of compiled program objects and libraries and create the overall library or executable. Then you have CL get program info, which can actually return you back some information about an already compiled and created program object, or you can CL get program build info, which will give you build information about the process that was followed and all that for creating the program object for each device, right? So these are like so the first three would be standard compilation link programs. Again, it is useful if you want to do these things by the host program, right? Or if you want the information extracted from the program object that is available in the context in the runtime, then you would need to execute these last two commands. So what's a kernel object? A kernel function is declared in the program. The kernel is identified by this kernel __ kernel qualifier, as we have seen earlier. Now the corresponding kernel object encapsulates this function which is declared in the program, and also it encapsulates the argument values to be used when this kernel function would be executed. So just for manipulation of kernel type objects, you again would be having some specific OpenCL API support. For example, you want to create the kernel object, or you want to create kernel objects for all kernel functions in a program. In a program, of course, you can have multiple kernel functions. And the next important thing is, if you want to set the argument values of a kernel. Now, we know that for a function we have to specify a set of arguments. Now, the way it is done for an OpenCL kernel is you fire multiple instances of CL set kernel argument to, with each instance you add in a new argument value, right, for a specific argument of the kernel. And if you want to get information about the kernel object, that you can get from CL get kernel info. If you want argument information about the kernel, you can get it from CL get kernel arg info, return information about the arguments of a kernel. And then if you want to enqueue a command which will actually execute a kernel in a device sitting in a context, for that the actual command is clenqueue ndreg kernel. So you are enqueuing. So since this is an enqueuing of a command, as we have understood, unlike CUDA where you just launch a kernel, here things are a bit more system specific, right? So even a kernel execution is a generic OpenCL command. So it's basically known by the name clenqueue ndrange kernel. Since it's a queuing operation, you don't really get to execute it directly. You enqueue an execution type command in a command queue. That's why you call it clenqueue ndrange kernel. So let's see how the OpenCL host code actually continues from the point where we left, where we just identified the platform IDs and the device IDs. So and also we created a context with a single GPU type device, right? So the first thing we'll be doing is we are going to build the program object. So for that we will be firing this CL create program with source command, where we will be providing this as you can see, ignore the other arguments, but observe this argument here, which is characters. This is the character array argument. So essentially kernel source is like a character array which is containing the actual source code of the kernel. Fine. So with this program you get with this function create program with source, you are expecting that character array to be passed containing the real source code, and it's creating the program out of it, right? Now once you have the program object, since in this is the type of compilation we are following here, that you are going to build the program object from the source. That's why we fired this function as we discussed earlier. If you are already having the binary available, then or the intermediate code available, the other options of CL create program would be used, as we have seen earlier. In this case we are just showing this example, and then once the program object is ready, you would like to build it. Let's compile and link. So since the object is with name is program, it's of type CL underscore program. This is the type, the OpenCL type for program objects. The next you execute this command to build it, right? So once that build of the program object is done, you have to create the actual kernel objects which are going to be enqueued for execution, right? So now you pass this program object that has been built to the CL create kernel command, and it will return you this OpenCL kernel type object KOV add. So this is how you create a kernel object finally using the CL create kernel. Before that you build the program. Before building the program you create the program object. So again I will just repeat, we are considering that kernel is available as a source in a character array. Use that to create program object, use that to build the program, use that to create the kernel. Once the kernel object is created, now the other thing is, just like kernel, you also need the memory space to be declared as buffer objects. So these are stored as block of contiguous memory like normal C, and they are used as general purpose object to hold built-in types like int, float, vector types, or you can also have a user defined type, right, in the OpenCL program. They can be manipulated through pointers much as one would with any block of memory in C. Now of course also it stores essentially it's a one-dimensional collection of elements like C arrays, right. Elements of the buffer object can be a scalar data type or a user defined structure, as we know. Now one thing I would like to point that most of this information we have mined out from the Chronos specification that is available in the Chronos website. So that's quite openly available. Most of this information has been mined out from those sources, and also the references we have provided at the end of these presentations, right. Now if I am trying to create some buffer objects, just like for kernel objects we have a set of commands to execute, for buffer objects again we have some commands to execute. So first you have the CL create buffer which will create the buffer objects. You have enqueue buffer through which you can enqueue commands pertaining to read or write to be done on buffer objects, right? So, for example, CL enqueue read buffer, this would enqueue commands to read from a buffer object to the host memory. So that's important, right? You have the host, you have one of the devices identified as your host device. So you want to read back data that has been computed on the device by an OpenCL kernel. Now the buffer object is pertaining to the memory region in that device in which the OpenCL kernel has executed. So to read from that to the host side memory, you have to execute a command, right? Again, I will say that unlike a CUDA command for read or write to and from the host program, things are like here you have to enqueue a read command, you have to enqueue a write command, right? So if you have to read from the device side buffer object to the host side memory, you enqueue a read command, CL enqueue read buffer. You have to write from the host memory to the device side buffer object, you will have a CL enqueue write buffer, right, to write to the buffer object from the host memory, right? Now, of course, I mean, you have to remember that we are not talking about normal GPU things here, like CPU, GPU based CUDA execution. Like it can also be that the host and the device have a shared memory space, right, on which things are going on. We will see such some examples of such kinds of devices later on. Now, coming here, so apart from CL enqueue read and write buffers, you also have this CL enqueue copy buffer. So essentially, you can copy a buffer object, identify a source to destination or some destination buffer. You can also fill a buffer with a pattern if you give a pattern and a pattern size. And also you have the map operation to map a region of the buffer object into the host address space and return a pointer for this mapped region. So you have a region of the buffer object which you can map to the host address space and return the pointers, right? So that is also something that would be possible. So these are the different buffer manipulation commands that are there. Maybe with this we'll like to end this presentation. Thank you.